Breaking, Japan has just seen 5 powerful earthquakes, each between magnitudes 5.5 and 6.8, striking the same fault lines that unleashed the catastrophic 2011 tsunami. Scientists say this cluster should not even be possible under normal rules, and the pattern echoes warning signs from before Japan's last mega-quake. If the next one reaches magnitude 8, the impact could be thousands of times more destructive than what we have seen so far. Urgent. Is this the start of another national catastrophe or a statistical fluke? The answer may hinge on the restless forces now building beneath Japan. Seismologists tracking Japan's latest earthquake swarm are watching numbers that break the usual rules. In a typical sequence, a main shock like the recent magnitude 6.8 would be followed by aftershocks that quickly drop off in strength, often no stronger than about magnitude 5.8. But over just a few days, 5 separate earthquakes have struck between magnitude 5.5 and 6.0, each one unusual for an aftershock. The official catalog now lists 5.5, 5.6, 5.7, 5.9, and 6.0, all clustered tightly along the same fault system. This pattern runs against the expectations set by the Gutenberg-Richter law, which predicts a rapid decay in aftershock size after a main earthquake. Instead, the swarm's upper limit keeps matching or even exceeding the expected cap, raising the question of whether these are aftershocks at all or signs of something more serious brewing underground. Dr. Noriko Kamaya, a senior seismologist at the Earthquake Research Institute in Tokyo, explains it this way. For a magnitude 6.8 event, the strongest aftershock should rarely go above magnitude 5.8. When you see multiple earthquakes clustering at or above that level, it is not just statistically rare. It is a signal that the system is not behaving normally. This anomaly is now at the center of scientific scrutiny, with monitoring agencies recalculating probabilities in real time as the swarm continues. Anomalous swarm and historical echo. In March 2011, the northeast coast of Japan experienced a seismic buildup that would change modern disaster science. 2 days before the main catastrophe, a magnitude 7.3 earthquake struck off the Tohoku coast, shaking coastal towns but causing only minor damage. At the time, many experts classified it as a significant event but not a harbinger of disaster. Seismologists at the Earthquake Research Institute in Tokyo noted the clustering of activity along the Japan Trench, a segment notorious for mega-thrust ruptures. The foreshock epicenter lay just south of where, on March 11, 2011, the magnitude 9.1 main shock would rupture the plate boundary, unleashing a tsunami that devastated hundreds of kilometers of shoreline. Archival data and contemporary reports confirm that the 2011 sequence followed a recognizable pattern, a series of moderate to strong foreshocks, culminating in a sudden massive release of tectonic energy. The spatial overlap between the magnitude 7.3 foreshock and the magnitude 9.1 main shock traced a clear line along the trench, matching the current zone of seismic unrest. Researchers mapped these events and found the same segment lighting up again. They caution, however, that while such patterns echo past disasters, they do not guarantee a repeat. The 2011 events remain the textbook case of how a foreshock can precede a megaquake, but each sequence is unique, and the science of prediction remains probabilistic, not prophetic. Along the northern arc of the Pacific, tectonic stress rarely stays put. Major earthquakes in the Kamchatka subduction zone, some reaching magnitude 8.8 in the last 2 decades, have sent their influence far down the fault lines toward Japan. Earthquake modelers at JAMSTEC and the University of Tokyo turn to Coulomb stress transfer maps to understand what that means for Japan's seismic future. These models use detailed fault geometry and slip data from recent Kamchatka ruptures, running calculations that show how stress redistributes through the crust. The July 2025 Kamchatka event, for example, released enough energy to alter the balance along the Japan Trench, shifting the stress landscape by measurable amounts. On the latest Delta CFF maps, wide swaths off Honshu's Pacific coast now show positive stress changes, regions where the crust has been nudged closer to failure. Dr. Shunpei Watanabe, a senior modeler, explains that they input slip distributions from the Kamchatka event, apply realistic friction coefficients, and run scenarios for different crustal structures. The results are clear. Several segments of the Japan Trench are now under increased load. Sensitivity tests, varying the friction and fault parameters, consistently highlight the Northern Trench as a zone of heightened risk. While these models are powerful, they are no guarantees. Static Coulomb stress calculations capture only a snapshot, and dynamic stress, viscoelastic relaxation, and other factors can shift the picture over time. But the mechanical rationale is straightforward. With each major rupture to the north, Japan's subduction faults receive an extra push. In this context, even moderate local disturbances could have outsized consequences if the system is already near its breaking point. At 7:15 UTC on November 9th, a powerful X-class solar flare erupted from an active sunspot, sending a full halo coronal mass ejection hurtling toward Earth. Within hours, Japan's geomagnetic monitors recorded a rising G index, with the KP index moving into G2 and G3 minus territory. At 8:03 and 8:54 UTC, two significant earthquakes, magnitude 6.8 and 6.4, struck off the Honshu coast, just as the region sat beneath the main geomagnetic footprint of the event. The timing was precise enough to trigger immediate discussion inside Japan's National Operations Center, where supervisors tracked both the seismic and space weather feeds in parallel. Precise timing, CCR1 chronograph imagery confirmed the CME trajectory, while ACE and DSCOVR satellites registered solar wind fluctuations. In the hours that followed, radio traffic and internal logs captured the tense, data-driven debate over whether the solar flare could have acted as a trigger for the seismic activity. Tense debate. Statistically, the overlap is rare, but not unprecedented. Historical Poisson tests show that the likelihood of a magnitude 6.8 earthquake occurring within 500 minutes of an X-class flare is less than 1% under normal background rates. Cross-correlation analyses, however, yield a coefficient well below 0.2, too weak for most experts to claim a direct physical link. Statistics. Seismologists at JMA and the Earthquake Research Institute remain cautious, emphasizing that while the proximity and time is striking, no deterministic mechanism has been proven. Heliophysicists and a minority of seismologists point to possible ionospheric or electromagnetic effects, but the majority view remains skeptical. As the Operations Center continues to monitor both seismic and solar data, the scientific debate over cause and coincidence remains unresolved. A magnitude 7 earthquake in this region would already unleash severe shaking across hundreds of kilometers, but the difference between magnitude 6.8 and magnitude 8.0 is far more than a simple step up. On the logarithmic moment magnitude scale, each full number increase means 32 times more energy is released. The leap from magnitude 6.8 to magnitude 8.0 is a jump of 1.2 units, enough to multiply the energy by over 60 times. In practical terms, if the current sequence escalates to magnitude 8, the ground motion and rupture length would expand dramatically, threatening infrastructure and communities far beyond the immediate epicenter. The 2011 Tohoku earthquake, at magnitude 9.1, released nearly 2,000 times the energy of a magnitude 6.8. Even a low-end magnitude 8 would strain emergency response and test the limits of preparedness, with the potential for widespread disruption on land and at sea. Japan's official earthquake risk assessment leaves little room for comfort. Government panels now put the chance of a magnitude 8 or larger megathrust earthquake along the Nankai Trough at 75 to 82% over the next 30 years, a probability that has only crept higher with each new seismic cluster. In the worst-case scenario, government models predict up to 298,000 deaths and economic losses reaching 292 trillion yen, driven by tsunami inundation, structural collapse, and cascading fires. These numbers are not theoretical. They come from disaster simulations used for national policy and emergency planning. The urgency is sharpened by the fact that 2025 is already among the most seismically energetic years on record, with Japan's tectonic stress at a historic high. For scientists and officials, the message is clear. The odds are not abstract. They are a warning grounded in decades of data and lived experience. Right now, Japan faces a seismic probability. Over 70% chance of a magnitude 8+ quake within 30 years. With solar storms and tectonic pressure converging, the clock is ticking in real time. Preparedness is not just policy. It is survival. The Earth does not give warnings twice.